Consider the scene in November 1918, as engineers across the European continent grappled with an intractable dilemma. The Great War had concluded, yet its stark lesson was indelibly etched into every ravaged battlefield, from the blood-soaked fields of Verdun to the desolate expanses of the Somme. Conventional wheeled vehicles alone could no longer dictate the outcome of military campaigns. Trucks invariably became mired in the treacherous terrain, while tanks frequently suffered debilitating mechanical failures. Despite these formidable obstacles, armies still faced the imperative task of rapidly transporting personnel and material across landscapes that bore an uncanny resemblance to the pockmarked surface of the moon. Our compelling narrative commences at the curious juncture where two seemingly irreconcilable concepts converged, bound by an unforeseen necessity. The innovative concept of the half-track did not materialize spontaneously from a vacuum. Its genesis can be traced back to 1915, when a gifted French engineer named Adolphe Cagrès was in the employ of Tsar Nicholas II in Russia. His primary objective was to ensure the operational mobility of the imperial family's automobiles amidst the formidable challenges posed by the deep Siberian snows. Cagrès' ingenious solution involved the pragmatic replacement of the vehicle's rear wheels with flexible rubber tracks, while judiciously retaining the front wheels to facilitate steering. This approach was characterized by its elegant simplicity and remarkable efficacy. By 1919, the renowned automotive manufacturer Citroën had acquired Cagrès' patents and commenced the production of vehicles incorporating the Cagrès-Hinton system, thereby unequivocally demonstrating the hybrid design's superior capability in traversing terrain that proved insurmountable for purely wheeled conveyances. At this nascent stage, however, the military applications of this technology were not yet a primary consideration. Its initial purpose was solely to enable efficient transit from point A to point B when confronted by the prohibitive dictates of nature. Stay with us and watch the end of the video. We will be grateful for your like and subscription. As the 1920s unfolded, military strategists began to pose increasingly uncomfortable questions regarding the existing state of mechanized warfare. Tanks, while undeniably potent, were notoriously sluggish. The British Mark V, for instance, could barely achieve a speed of 4 miles per hour on an exceptionally favorable day. Conversely, trucks offered greater velocity, but became utterly ineffectual the moment they deviated from paved thoroughfares. Infantry units continued their arduous marches on foot, a practice largely unchanged since the Napoleonic era, which invariably meant that armored formations would surge ahead only to be compelled to halt and await the arrival of the rifle-wielding ground troops. Even amidst their post-war setbacks, German engineers were already meticulously sketching novel designs. The Soviets, too, were actively engaged in experimental endeavors. Even the Americans, who had made only limited use of tanks during the First World War, embarked upon their own design explorations at the venerable Rock Island Arsenal. The profound allure of half-tracks lay in their audacious engineering compromise. They offered approximately 70% of a tank's formidable off-road prowess, while simultaneously retaining around 80% of a truck's inherent speed and mechanical straightforwardness. The presence of front wheels afforded competent steering capabilities, obviating the need for complex track braking mechanisms. The expansive rear tracks efficiently distributed the vehicle's substantial weight across challenging surfaces such as mud, sand, or snow. Furthermore, precisely because power was not being transmitted to all four corners via tracks, the entire assembly remained lighter, more cost-effective to produce, and considerably simpler to maintain than a fully tracked tank. In 1931, the United States Army conducted trials of the Cunningham T1, essentially a conventional truck retrofitted with tracks appended to its rear. Its appearance was undeniably peculiar, yet it effortlessly navigated trenches that would have completely immobilized standard trucks. By the mid-1930s, the harsh realities of modern conflict were becoming increasingly apparent. Germany was surreptitiously rearming, notwithstanding the stringent limitations imposed by the Treaty of Versailles. Japan was aggressively expanding its territorial claims into China, deploying formidable mechanized columns. The Spanish Civil War, raging from 1936 to 1939, served as a crucial proving ground where all belligerents absorbed the same unvarnished truth. Contemporary warfare necessitated that infantry units maintain pace with armored formations, and they needed to arrive at the point of engagement prepared to fight, rather than utterly spent from a grueling 20-mile march. The half-track had transcended its status as merely a clever invention. It was rapidly evolving into an indispensable military asset. Engineers in bustling Detroit, industrial Stuttgart, and sprawling Moscow were engaged in an intense race to unravel the same complex conundrum: how to construct a vehicle that could engage like a tank, transport like a truck, and fire like artillery, all while adhering to a production cost that would permit the manufacturing of thousands of units. This pivotal question would ultimately define the formidable machines that would subsequently roll into Poland, France, North Africa, and eventually traverse half the globe. The hybrid warrior was poised to embark upon its decisive role in the impending global conflict. The American approach to resolving the half-track problem mirrored their characteristic industrial philosophy of the 1930s, an unwavering focus on mass production from the very outset. While their European counterparts meticulously crafted bespoke, specialized solutions, engineers at the White Motor Company in Cleveland and Autocar in Pennsylvania were conceptualizing assembly lines capable of churning out vehicles by the thousands. This strategic foresight culminated in the development of the M2 and M3 half-track family, machines that presented a brutally simple exterior, yet concealed remarkably ingenious engineering beneath their utilitarian, boxy steel panels. Let us commence with the power plant. White Motor ultimately selected the Hercules JXT inline six-cylinder engine, a 386 cubic inch gasoline-fueled motor that generated a respectable 147 horsepower at 2,800 revolutions per minute. While this figure might not appear particularly impressive when juxtaposed with contemporary engines, its crucial advantage lay in its unwavering reliability. It could be manufactured with remarkable speed, and mechanics already familiar with civilian trucks possessed the requisite expertise to service it efficiently. The engine was conventionally situated at the front, in the manner of a standard truck, which facilitated straightforward heat management and allowed for accessible maintenance without necessitating the dismantling of the entire vehicle. Maximum road speed achieved approximately 45 miles per hour, diminishing to around 25 miles per hour during cross-country travel, contingent upon the prevailing terrain. This velocity was sufficient to keep pace with tank columns, yet not so excessive as to subject the 10 infantry soldiers seated in the rear compartment to a relentlessly jarring and uncomfortable ordeal. The transmission system represented a significant achievement where White's engineers truly demonstrated their exceptional skill. They devised a 4-speed manual gearbox complemented by a 2-speed transfer case, furnishing the driver with a comprehensive total of 8 forward gears, in addition to 2 reverse gears. This extensive range empowered the vehicle to ascend a formidable 60% grade in first low gear or to effortlessly cruise at highway speeds in fourth high. Power was efficiently transmitted from the gearbox to a front axle dedicated to the wheels, and a separate drive shaft extended rearward to the track assembly. The front wheels possessed the capability to pivot normally for steering, but here lay a clever innovation. The driver also had access to independent brake pedals that could selectively slow individual tracks, thereby enabling significantly sharper turns than could be achieved by the front wheels alone. Mastering this nuanced control required considerable skill, but experienced drivers could practically execute pivot turns in situ. Now, turning our attention to the track system itself, this is where American pragmatism truly shone through. In contrast to the metallic links characteristic of tank treads, the M2 and M3 employed innovative rubber block tracks developed by the Firestone Tire and Rubber Company. Each track was ingeniously constructed from steel cable embedded within a robust rubber matrix, with 110 individual rubber blocks meticulously vulcanized onto the cable. These blocks measured approximately 5 inches in width and were specifically contoured to provide superior grip on dirt, mud, or snow. The brilliance of this design was multifaceted. Firstly, rubber tracks produced considerably less noise than metal clanking against metal, a critical advantage for tactical movement. Secondly, rubber exhibited greater durability on paved roads, avoiding the rapid wear and tear that metal tracks inflicted upon both themselves and the road surface. Thirdly, in the event of localized damage, individual blocks could be replaced in the field, eliminating the need to swap out entire track assemblies. The suspension system was a modified vertical volute spring arrangement, essentially comprising large coil springs mounted vertically behind each of the 4 road wheels on every track assembly. As the vehicle traversed obstacles, these springs compressed, effectively absorbing the shock. Was the ride smooth? Candidly, no. Riding in the rear of an M3 over rugged terrain was akin to being inside a cement mixer, yet the system proved remarkably effective. It was straightforward to maintain, and crucially, it distributed the vehicle's substantial 20,000-pound combat weight across a sufficient surface area to maintain ground pressure at approximately 10 pounds per square inch. For context, a fully loaded conventional truck might exert 40 psi, which elucidates why trucks often became mired in mud while half-tracks steadfastly continued their advance. Production escalated at an astonishing pace once America formally entered the war in December 1941. The manufacturing facilities of White Motor, Autocar, and Diamond T were collectively churning out an impressive 500 half-tracks per month by mid-1942, a figure that soared to an astounding 1,500 units monthly by 1943. Total production across all variants ultimately surpassed 41,000 units by 1945. This prodigious output underscores the profound ingenuity of the American approach. These machines may not have been the most exquisitely engineered half-tracks ever conceived, but they were demonstrably good enough, and their sheer numerical availability from the assembly lines arrived precisely when the Allied armies most desperately required them. While American engineers meticulously pursued designs optimized for mass production, their German counterparts were consumed by an entirely different objective: the relentless pursuit of technical perfection, irrespective of the associated costs. The Sonderkraftfahrzeug 251, more commonly recognized as the SD, KFC 251 or simply Hanomag, after its principal manufacturer, embodied a fundamentally antithetical design philosophy, where the Americans embraced the maxim, "Good enough is good enough." The Germans insisted that every mechanical component be engineered to its absolute theoretical limit. This uncompromising approach resulted in half-tracks that were phenomenally capable, yet concurrently absurdly intricate and costly to construct. The veritable heart of the SD, KFC 251 was a Maybach HL42 TUKRM 6-cylinder gasoline engine, which generated 100 horsepower, a figure notably less than its American Hercules counterpart. However, A crucial distinction emerges here. Maybach was the very same prestigious company responsible for manufacturing the engines powering the formidable Tiger and Panther tanks. Consequently, this was not merely a repurposed truck engine pressed into military service. The HL-42 was meticulously engineered specifically for tracked vehicles, with scrupulous attention devoted to optimizing torque delivery at lower RPMs. This powerful engine propelled the 8.5-ton vehicle to a maximum speed of 53 km per hour on roads, remarkably, even faster than the American M3, although its cross-country performance remained nearly identical at approximately 20 to 25 km per hour. The German engine operated at cooler temperatures and with greater fuel efficiency than its American equivalent, but it demanded more frequent and meticulous maintenance and relied upon precision-engineered components that required significantly longer manufacturing times. German transmission engineering often bordered on what could be described as over-engineering. The SD, KFZ 251 utilized a sophisticated Maybach Variarex 128H preselector gearbox, boasting an impressive 7 forward speeds and 3 reverse gears. Let that specification truly resonate. 7 distinct forward gears. The driver would pre-select the desired next gear using a dedicated lever, then momentarily depress the clutch pedal, at which point the transmission would execute the shift automatically via an intricate vacuum system. When operating flawlessly, this system offered a smoother and faster shifting experience than the manual transmissions found in American vehicles. However, when it inevitably malfunctioned, which regrettably occurred with greater frequency, it necessitated the intervention of a highly specialized mechanic and replacement parts that could often take weeks to procure. This encapsulates the German half-track narrative in microcosm, technically superior in concept, yet logistically nightmarish in practice. I am from a quiet village nestled in the heart of the countryside, a place far removed from the roar of engines and the clamor of war. The video topic is fascinating, offering a deep dive into the engineering compromises and strategic decisions that shaped military technology. It's truly eye-opening to see how different nations approach the same problem with such divergent philosophies, from mass production to technical perfection. It makes one appreciate the complexity of warfare and the ingenuity required to overcome its challenges. The logistical challenges presented by the SD, KFZ 251 half-track were indeed formidable, bordering on the nightmarish. The German approach to track design offered a significant insight into their engineering philosophy. Unlike the rubber block cable tracks commonly found in other nations' half-tracks, the SD, KFZ 251 utilized metal track links, meticulously joined by pins, mirroring the robust construction of tank tracks, albeit in a more slender form. Each side of the vehicle was equipped with 70 such track links, forged from manganese steel and meticulously shaped with grooves to optimize grip. These metal tracks exhibited exceptional durability on unyielding surfaces and could withstand an astonishing degree of abuse. However, this resilience came at the cost of considerable noise generation and a propensity to inflict damage upon paved roads. Furthermore, they necessitated continuous tension adjustments and rigorous maintenance. The German engineers consciously embraced these trade-offs, prioritizing the superior performance of metal tracks in the most unforgiving environments, such as deep mud, heavy snowfall, and extreme cold, where rubber components were prone to cracking and catastrophic failure. Yet, it was in the innovative interleaved road wheel system that German engineering truly distinguished itself. Most half-tracks, including their American counterparts, typically featured a simpler arrangement of 4 or 5 road wheels per side, mounted on straightforward suspension arms. In stark contrast, The SD, KFC 251 boasted a sophisticated configuration of 7 overlapping road wheels per side. These wheels were arranged in such a way that those from opposing sides interlaced, creating a distinctive zigzag pattern when viewed from the rear of the vehicle. This interleaved design conferred several distinct advantages. It facilitated a more uniform distribution of the vehicle's weight, further reduced ground pressure, and, remarkably, provided an exceptionally smooth ride for a tracked vehicle. German soldiers, who had experienced both captured American half-tracks and their indigenous Hanemags, consistently expressed a preference for the German suspension, attesting to its genuinely superior comfort and performance. After 2 or 3 paragraphs, ask us to stay with us and watch the end of the video. We will be grateful for your like and subscription. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. The brilliance of the interleaved wheel system, however, was inextricably linked to a significant drawback. It was a veritable catastrophe from a maintenance perspective. Should an inner wheel suffer damage or require replacement, a tedious and time-consuming process of removing multiple outer wheels first was unavoidable. Furthermore, in challenging conditions, particularly on the eastern front where temperatures plummeted to -40°C, mud, snow, and ice would readily accumulate between the wheels, freezing solid overnight. German crews were frequently compelled to spend countless hours each morning, armed with hammers and blowtorches, simply to free the wheels. A task that might be completed in a mere 15 minutes on an American half-track could easily consume half a day's effort on a Hanemag. The complexity inherent in the SD, KFZ 251's mechanical design was mirrored by its manufacturing demands. In 1940, the construction of a single SD, KFC 251 required approximately 3,000 hours of skilled labor, a stark contrast to the roughly 800 hours needed for an M3 half-track. Throughout the entire duration of the war, Germany managed to produce approximately 15,500 SD, KFC 251s. While this figure is commendable given their industrial constraints, it represents barely a third of the American production output. This disparity vividly illustrates the German emphasis on quality over quantity, a philosophy concretely embodied in steel and rubber. Now, the narrative takes a truly remarkable turn. Someone conceived the audacious notion of affixing artillery pieces to these sophisticated trucks. This idea, initially appearing outlandish, gains logical coherence when one considers the fundamental challenge of traditional artillery. Conventional artillery pieces were typically towed by trucks or horses, a method that inherently protracted setup times. Moreover, the ability to rapidly reposition to evade counter-battery fire was severely hampered. By directly mounting the same gun onto a half-track chassis, a new paradigm of mobile firepower emerged, capable of firing, relocating swiftly, and thus enhancing its survivability. Yet, the engineering hurdles presented by this concept were undeniably brutal. The primary obstacle revolved around the immense forces generated by recoil, which threatened to utterly destroy the vehicle. When a 75 mm gun discharges, it instantaneously generates approximately 15 tons of rearward force. This tremendous energy must be effectively managed. Simply bolting a cannon to a half-track's cargo bed would inevitably result in the vehicle being torn apart or even flipped backward by the recoil. American engineers, engaged in the development of the M3 gun motor carriage in early 1941, devised an ingenious multifaceted solution. They mounted a French 75 mm gun onto a heavily reinforced pedestal, which was directly welded to the vehicle's robust frame, rather than its less structural body. Complementing this, massive recoil cylinders, functioning essentially as hydraulic shock absorbers, were integrated. These allowed the gun barrel to retract backward by about 2 feet upon firing, thereby transforming the violent 15-ton impulse into a more manageable, sustained push distributed over a full second. But the intricate dance with physics did not end there. The principle of equal and opposite reactions dictated that even with sophisticated recoil management, the act of firing would inevitably cause the entire vehicle to rock. The innovative solution came in the form of outriggers and spades, metal legs designed to swing down from the sides and rear of the vehicle, terminating in flat plates that would dig firmly into the ground. Prior to firing, the crew would deploy these stabilizers, effectively anchoring the half-track in position. The M12 gun motor carriage, a formidable vehicle that mounted a 155 mm howitzer on a modified M3 chassis, incorporated an enormous spade at its rear. This spade had to be driven securely into the ground before each firing mission. Without this crucial stabilization, the sheer force of firing would literally propel the 26-ton vehicle backward by several feet with every shot. The Germans, in their SD, KFZ 251/9 variant, adopted a distinct strategy, mounting a short-barreled 75 mm gun within a limited traverse mount. Their objective was not to create a fully mobile artillery piece, but rather to construct an assault gun, a vehicle capable of accompanying infantry, engaging bunkers, or buildings at close range with devastating blasts, and then rapidly repositioning. The restricted traverse mechanism inherently reduced structural stress, as the gun could not pivot sufficiently to destabilize the vehicle. With a maximum elevation of only 20 degrees, this weapon was not designed for lobbing shells over distant hills. Instead, its purpose was direct fire against visible targets, typically within a range of 800 meters. The challenge of ammunition storage presented yet another formidable hurdle. A conventional artillery piece might have its ammunition carefully stacked nearby in a protected position. However, on a half-track, every single shell travels with the vehicle, rendering robust armor protection absolutely essential. The M12 GMC, for instance, could internally carry a mere 10 rounds of 155 mm ammunition, primarily because each shell weighed a substantial 95 pounds and occupied considerable space. Consequently, these vehicles typically operated in conjunction with an accompanying M30 cargo carrier half-track, which followed closely behind, laden with an additional 40 rounds. German vehicles encountered similar constraints. The SD, KFZ 251/9 could accommodate only 52 rounds of 75 mm ammunition, which were meticulously stored in bins along the hull's sides, where the armor was thickest. The development of anti-aircraft variants pushed the boundaries of engineering even further. The M16 multiple gun motor carriage, for example, mounted 4.50 caliber machine guns within an electrically powered turret, thereby creating a highly mobile flak platform. The entire turret system, including its integral generator, weighed over a ton and was positioned high on the vehicle, significantly impacting its center of gravity. Engineers were compelled to incorporate counterweights and slightly widen the track stance to prevent the vehicle from tipping during sharp turns. The combined rate of fire for the 4 machine guns was an impressive 2,400 rounds per minute, a figure that, while sounding formidable, translates to a consumption of 200 pounds of ammunition per minute. The M16 carried a total of 5,000 rounds, affording approximately 2.5 minutes of continuous firing before the ammunition supply was exhausted. This meant that the majority of the vehicle's interior space was dedicated to storing boxes of linked ammunition. Perhaps the ultimate manifestation of this concept was the SD, KFZ 251/22, a German development from 1944, which mounted a powerful 75mm Pak-40 anti-tank gun. This weapon possessed the capability to penetrate 100mm of armor at 1,000 meters, rendering it a grave threat even to formidable Soviet T-34 tanks. However, integrating such a potent gun onto a relatively light vehicle necessitated compromises across the board. Ammunition capacity plummeted to a mere 19 rounds. The gun shield provided only minimal protection, as additional armor would have overloaded the chassis. Furthermore, firing from any ground that was not perfectly level risked overturning the vehicle. Crews quickly learned the critical importance of careful positioning, understanding that their initial shot might be their sole opportunity before they were forced to relocate or face annihilation from retaliatory fire. Tank destroyers epitomized desperation engineering at its zenith. By 1942, both Allied and Axis forces were confronting tanks for which they had not adequately prepared. German Tiger tanks that effectively shrugged off the majority of Allied armaments, Soviet T-34s that overwhelmed German defensive positions, and Japanese armor in the Pacific that demanded a greater punch than infantry rifles could deliver. The core problem was straightforward. Constructing dedicated tanks required time and resources that were simply unavailable. The expedient solution of mounting anti-tank guns on existing half-track chassis offered a development timeline measured in months rather than years. The American M3 gun motor carriage represents, literally, the very first attempt at this concept, hastily assembled in 1941 even before the attack on Pearl Harbor. Engineers at the Aberdeen Proving Ground took standard M3 half-tracks, removed the bench seats from the rear compartment, and mounted a 75mm M1897 gun, a design originating from World War I, on a pedestal within the cargo area. There was no turret, no substantial protection, merely a gun shield and a fervent hope. The crew of 5 operated completely exposed from the waist up. Crucially, however, it possessed the capability to destroy German Panzer IIIs and early Panzer IVs at a range of 1,000 yards. Between 1941 and 1943, approximately 2,200 of these vehicles were manufactured. These vehicles first saw combat in North Africa, commencing in November 1942, where American forces at Kasserine Pass endured harsh lessons regarding German armor superiority. The performance of the M3 GMC in Tunisia starkly revealed the fundamental flaw of the half-track tank destroyer. While it could inflict damage, it was utterly incapable of absorbing it. The armor on its sides measured a mere 6.35 millimeters, barely sufficient to stop rifle rounds, and utterly useless against anything heavier. German gunners quickly identified M3 GMCs as priority targets. Eliminating one early on meant neutralizing a significant threat. American after-action reports from the battles around Sidi Bouzid in February 1943 unequivocally demonstrated that M3 GMCs were compelled to fire from concealed positions at least 1,200 yards away, constantly utilize their mobility to reposition, and absolutely never allow themselves to be caught in the open. They were, by necessity, ambush predators, not brawlers. I am from a digital realm. Regarding the video topic, the engineering compromises and innovative solutions discussed highlight the relentless ingenuity and stark realities of wartime development, showcasing how necessity truly became the mother of invention under extreme pressure. The German military, recognizing an urgent operational gap, developed its own specialized half-track vehicles for engaging enemy armor, viewing them as tactical hunters rather than direct combatants. This initiative arose from the brutal realities of the Eastern Front, where by the close of 1943, the sheer volume of Soviet tank production was relentlessly pressing against and ultimately overwhelming German defensive formations. Initially, the SD, KFZ 251 out of 10, equipped with a 37mm PaK-36, proved woefully inadequate. This anti-tank gun was already considered obsolete and could do little more than superficially mar the frontal armor of a formidable T-34 tank. Driven by an acute need for a more effective solution, German engineers conceived the SD, KFZ 251/22, which ingeniously mounted the potent 75mm PaK-40, the very same weapon system found on their purpose-built tank destroyers. Production of this new variant commenced in 1944, with approximately 175 units ultimately constructed before the cessation of hostilities. This particular iteration of the half-track possessed the genuine capability to pose a serious threat to Soviet armored vehicles, boasting impressive penetration values that could reach 133 mm at a range of 500 meters when utilizing standard ammunition. Such firepower was sufficient to pierce the hull or turret of a T-34 across most typical combat distances. However, the integration of such a formidable weapon onto a half-track chassis inherently introduced a series of severe engineering compromises. The PaK-40 gun alone weighed a substantial 1,425 kilograms, equating to over 3,100 pounds. When factoring in the weight of its specialized mount, protective shield, and the necessary ammunition, the total combat load imposed on a vehicle originally engineered for transporting infantry easily surpassed 2 tons. Consequently, the SD, KFZ 251/22 became markedly nose-heavy, exhibited poor handling characteristics, and its suspension system was placed under constant, extreme stress. Its maximum operational speed plummeted to a mere 40 km per hour, and its performance over rough, cross-country terrain suffered noticeably. German crews frequently reported that piloting a fully laden SD, KFZ 251/22 felt akin to wrestling a recalcitrant, stubborn horse, with the steering mechanism demanding immense physical exertion, especially when navigating through thick mud or deep snow. The practical application and tactical deployment of these vehicles underwent significant refinement through the crucible of combat experience. By 1944, both American and German military doctrines had converged upon strikingly similar operational principles for these improvised anti-tank platforms. We sincerely hope you are finding this exploration of wartime ingenuity compelling. We encourage you to stay with us and watch the end of the video for further insights. Your like and subscription would be greatly appreciated, helping us to continue producing content like this. Please also take a moment to write a comment about where you are from and what you think about the video topic. We value your engagement. Half-track tank destroyers proved most effective when strategically positioned in prepared defensive strongholds. From such locations, they could exploit natural terrain features for concealment and protection, engage advancing enemy armor at the maximum effective range of their weaponry, and then execute a rapid withdrawal immediately after firing. A prime example of this methodology was observed during the massive Soviet offensive known as Operation Bagration in June 1944. German SD, KFZ 251/22s were deployed in small, cohesive units, typically comprising 3 to 5 vehicles, which would be expertly concealed within tree lines or behind earthen embankments. Their operational procedure involved patiently waiting for Soviet armored columns to advance within an optimal range of approximately 800 meters, at which point they would unleash a concentrated volley of fire before swiftly displacing to prearranged alternate firing positions. The very survival of these crews and their vehicles was entirely contingent upon their mobility and the element of surprise, as remaining in a protracted engagement inevitably spelled destruction. A parallel evolution in tactical employment emerged from the American experience in France following the D-Day landings. The M3 GMCs provided crucial support for advancing infantry formations by establishing overwatch positions from elevated ridge lines, poised to intercept and neutralize German counterattacks. During the intense fighting around St. Lo in July 1944, M3 crews honed their coordination tactics with the heavier, purpose-built M10 tank destroyers. The lighter half-tracks would often act as bait, drawing German armor into revealing their positions, thereby allowing the more heavily armed M10s to deliver the decisive blows. This was undeniably hazardous work, often resulting in high casualties among the half-track crews, yet it was instrumental in preventing German armored thrusts from devastating American infantry positions. The half-track tank destroyer was never conceived as the ideal or ultimate solution. Rather, it was the most readily available and pragmatic option, hastily constructed and widely distributed because the only alternative was to confront enemy tanks armed with little more than bazookas and sheer courage. By late 1944, both Allied and Axis forces began to gradually phase out these improvised platforms in favor of more specialized, purpose-built armored fighting vehicles, but for a critical 2-year period, these hybrid creations filled an indispensable void. Beyond their temporary role as tank destroyers, if one strips away the heavy armament and the perceived glory of combat, the fundamental essence of the half-track's purpose becomes clear: to transport infantry safely to the front lines, ensuring they arrive alive and prepared for immediate engagement. This objective appears deceptively straightforward until one delves into the intricate engineering considerations, for the design of an armored personnel carrier inherently involves a delicate and often contentious balancing act between 3 mutually antagonistic requirements: protection, carrying capacity, and mobility. Should an excessive amount of armor be incorporated, the vehicle quickly becomes too heavy to maneuver effectively. Conversely, attempting to carry too many soldiers inevitably leaves insufficient space for essential ammunition, equipment, or even basic comfort. And if the design prioritizes speed above all else, the occupants are likely to perish the moment the first enemy machine gun opens fire. The M3 half-track specific armor scheme serves as a clear illustration of how these challenging calculations ultimately manifested. Its front plate consisted of 12.7 mm of rolled homogeneous steel, angled at a 30 degrees incline. Through the inherent principles of sloped armor physics, this arrangement provided effective protection roughly equivalent to about 15 mm of vertically oriented armor. This level of defense was generally sufficient to withstand standard 7.92 mm German rifle rounds at a range of 100 meters, and to largely deflect .30 caliber machine gun fire across most engagement distances. However, the side armor was significantly thinner, measuring a mere 6.35 mm, which offered only minimal protection against pistol rounds and shrapnel, but little else of consequence. The rationale behind such thin side plating was purely practical. Every additional millimeter of steel along the vehicle's considerable 18-foot length added hundreds of pounds to its overall mass. Engineers determined that 6.35 mm sides represented the absolute minimum necessary to offer crew and passengers a reasonable degree of safety from fragmentation and small arms, while simultaneously ensuring the vehicle remained light enough to maintain its crucial mobility, particularly across soft or uneven ground. The interior configuration was undeniably utilitarian and brutally practical. The driver and vehicle commander occupied individual seats in the front compartment, each protected by armored doors that could be swung open. Behind them, The main cargo area extended approximately 6.5 feet in width by 10 feet in length, fitted with simple bench seats running along each side. Here, 10 infantrymen would sit facing inward, often with their knees almost touching, their rifles held vertically or resting across their laps. This cramped arrangement was not arbitrary. It served a vital purpose: to keep the soldiers positioned safely below the protective height of the armored sidewalls. To stand upright meant exposing oneself from the chest upwards, rendering one vulnerable to a wide array of threats, from direct rifle fire to explosive shrapnel. Combat-hardened units swiftly learned the critical importance of remaining seated until the very last possible second before dismounting into action. The inherent open-top design of the half-track has been, and continues to be, a subject of extensive debate. The absence of a roof was dictated by three primary considerations: weight, visibility, and the imperative for rapid escape. Constructing a steel roof robust enough to offer meaningful ballistic protection would have added at least 800 pounds to the vehicle's mass, pushing it beyond its design suspension limits and significantly increasing its ground pressure. More critically, the infantry squad leader required an unobstructed view of the surrounding environment during movement to maintain situational awareness. Fully enclosing the vehicle would have meant effectively driving blind into potential ambushes. Furthermore, in the catastrophic event of striking a mine or sustaining a direct hit, an open top provided soldiers with the invaluable ability to bail out in mere seconds, rather than struggling to squeeze through narrow doors while the vehicle was potentially ablaze. Yet, the true revolutionary aspect of the half-track was not merely its engineering, but its profound impact on mechanized infantry doctrine. This is precisely where the half-track transcended its mechanical design to fundamentally alter the nature of warfare. Prior to 1940, infantry units either endured arduous marches or were transported in unarmored trucks, arriving at battlefields either physically exhausted or dangerously exposed. The advent of the half-track introduced an entirely novel tactical capability: infantry that could maintain pace with fast-moving tank columns and arrive at their objectives fresh, organized, and immediately ready to engage the enemy. During the pivotal North African campaign, specifically at El Alamein in October 1942, British and Commonwealth forces effectively utilized American-supplied M3s to closely follow their armored breakthroughs. This allowed them to swiftly exploit gaps in the German defenses before the enemy could effectively reposition and consolidate. The infantry, arriving fresh and fully equipped, were able to dismount and immediately secure objectives that tanks alone could not effectively hold. The D-Day landings in Normandy on June 6, 1944, further validated this concept under the most challenging possible conditions. American armored divisions deployed M3 half-tracks to push inland from the beaches, transporting infantry through the treacherous hedgerow country where tanks were particularly vulnerable. The typical tactical procedure involved half-tracks advancing in column behind Sherman tanks, maintaining a distance of 50 to 100 yards. When enemy fire erupted, the Shermans would immediately return fire, while infantry rapidly dismounted from the half-tracks, utilizing the vehicle's substantial bulk as immediate cover. This entire critical process, from initial contact to infantry on the ground and moving, often took no more than 15 seconds. German after-action reports from the Normandy campaign repeatedly highlighted the remarkable speed with which American mechanized units could react to enemy contact, a stark contrast to their own truck-mobile infantry, who were forced to dismount much farther back and advance on foot. The sheer numbers underscore the depth of this integration. A standard American armored infantry battalion in 1944 comprised 3 rifle companies, each organized into 3 platoons, with each platoon consisting of 4 squads. This totaled 36 infantry squads, necessitating 36 half-tracks for troop transport, in addition to command and support vehicles, bringing the total to roughly 50 half-tracks per battalion. These versatile vehicles were not merely troop carriers. They also transported crucial equipment such as .50 caliber machine guns, mortars, ammunition, radios, and vital medical supplies. In essence, the half-track transformed infantry from traditional foot soldiers into highly mobile, mounted troops, fundamentally revolutionizing the speed, flexibility, and overall tempo of mechanized warfare. By 1945, the strategic question was no longer whether to mechanize infantry, but rather how to design and construct the next generation of vehicles that could perform this essential role even more effectively. However, the true mettle of a machine designed in Cleveland for the battlefields of Europe was truly tested when it was thrust into the unforgiving Russian winter or the suffocating jungles of the Pacific. In these extreme theaters, every carefully calculated engineering assumption suddenly unraveled. The half-track's most significant trials were not conducted on controlled proving grounds in Maryland. They occurred amidst the brutal -40 mornings outside Stalingrad and on the relentlessly humid jungle trails of New Guinea. These exceptionally harsh environments necessitated an array of unanticipated field modifications, giving rise to numerous variants that often bore only a superficial resemblance to the original production vehicles. The Eastern Front, in particular, was where the theoretical robustness of the half-track collided with the grim realities of combat and climate in the most challenging possible ways. German SD, KFZ, 251s began experiencing catastrophic mechanical failures during the severe winter of 1941 to 1942, precisely as Army Group Center was pressing its relentless advance toward Moscow. Those aesthetically pleasing interleaved road wheels, which provided such a remarkably smooth ride in temperate conditions, transformed into veritable death traps when the pervasive mud froze solid overnight, firmly locking between the intricate wheel assemblies. Crews resorted to desperate measures, attempting everything from lighting fires beneath their vehicles to pouring precious gasoline between the wheels and igniting it, and even employing explosive charges in a desperate bid to blast the ice free. None of these improvised solutions proved consistently effective. Consequently, German field workshops began welding simple steel plates over the problematic gaps between the wheels, a modification that, while reducing overall performance, crucially prevented the accumulation of ice. By late 1942, factory production lines had incorporated design changes, featuring wider wheel spacing and a simplified suspension system, specifically engineered to better withstand the unique and brutal conditions encountered by units on the Eastern Front. American M3 half-tracks, supplied to the Soviet Union through the vital Lend-Lease program, encountered a distinct array of operational challenges upon their arrival. Between 1942 and 1945, approximately 1,100 M2 and M3 variants were delivered to the Russians, prompting Soviet mechanics to immediately embark on extensive modification efforts. The most pressing concern revolved around the vehicle's cold start capability. In the brutally frigid, sub-zero temperatures prevalent on the Eastern Front, the Hercules engine's carburetor was highly susceptible to icing, rendering ignition impossible without considerable and prolonged preheating. To counteract this, Soviet workshops ingeniously incorporated engine block heaters, meticulously insulated fuel lines, and recalibrated carburetors with adjusted jet sizes to effectively compensate for the denser, coal-thickened gasoline. Furthermore, they constructed rudimentary yet highly effective wooden enclosures over the open cargo areas, thereby transforming these open-top personnel carriers into enclosed vehicles that offered crucial, life-saving protection against the biting wind chill during arduous, extended movements. The efficacy of tracks in deep snow demanded singularly radical engineering solutions. Conventional rubber block tracks proved inadequate, as they would accumulate snow, which then compacted into solid ice, leading to a complete and debilitating loss of traction. Both German and Soviet forces engaged in extensive experimentation with grousers, which were robust metal cleats designed to bolt onto the track blocks, digging into snow and ice with a piercing grip akin to mountaineering crampons. The Germans, in particular, devised a comprehensive winter kit, comprising specialized track extensions that augmented the surface area by nearly 40%. This significant increase dramatically lowered ground pressure, enabling their vehicles to traverse snowdrifts deep enough to completely engulf standard wheeled vehicles. However, the installation of these kits was an arduous process, demanding many hours of labor in freezing conditions, and units that neglected this critical preparation before winter offensives often found their vehicles immobilized within a matter of days. The Pacific Theater, by stark contrast, presented an entirely different, yet equally merciless, set of environmental challenges. The relentless combination of intense heat and pervasive humidity relentlessly degraded electrical systems, accelerated the corrosion of metal components, and transformed vehicle interiors into stifling soundness capable of inducing severe heat exhaustion in mere minutes. Commencing in 1943, American forces operating in New Guinea confronted terrain that initially rendered half-tracks seemingly useless. Dense, impenetrable jungle, constricted pathways, treacherous swamps, and numerous unbridged rivers. Nevertheless, Marine and Army units demonstrated remarkable ingenuity in discovering creative applications for these vehicles. Engineers, for instance, completely removed the front wheels from some M3s and extended the tracks forward, thereby creating fully tracked vehicles with a significantly lower ground pressure, ideally suited for navigating marshy swamp crossings. While these field-modified behemoths appeared unconventional, even absurd, they possessed the unique ability to traverse mud that brought all other forms of transport to a grinding halt. We invite you to stay with us and watch the entire video. Your like and subscription would be greatly appreciated. Please share in the comments where you are from and your thoughts on the video's topic. Japanese forces, upon encountering American half-tracks during the Philippines campaign in 1944 to 1945, were genuinely perplexed by their design and utility. Japanese military doctrine at the time placed a strong emphasis on lightweight tanks and infantry transported by trucks, leading them to perceive half-tracks as unnecessarily complex and inherently maintenance-intensive. Their assessment, in tropical conditions, was not entirely unfounded. The sophisticated American and German half-tracks indeed demanded unremitting and constant maintenance in such environments. Pervasive humidity corroded delicate electrical connections, jungle mud infiltrated every bearing and joint, and organic debris frequently clogged critical cooling systems. Consequently, units deployed in these challenging theaters learned to conduct twice-daily maintenance routines, a regimen that essentially amounted to a comprehensive rebuilding of vital systems every few weeks to ensure operational readiness. Captured vehicles often yielded fascinating insights into battlefield adaptation and improvisation. The Soviets, for example, seized hundreds of German SD, KFC 251s during their major offensives of 1943 to 1944, immediately pressing them into service despite acute shortages of both ammunition and spare parts. Soviet crews, in a testament to their resourcefulness, welded on supplementary armor plates scavenged from destroyed tanks, creating formidable, albeit heavier and slower, Frankenstein vehicles that offered enhanced protection. Some Soviet-operated Hanemags underwent even more radical transformations, receiving entirely new armaments such as 85mm recoilless rifles, Katyusha rocket rails, and even flamethrowers. While these modifications would undoubtedly have horrified the original German engineers, Soviet military doctrine consistently favored maximum firepower and combat effectiveness over strict mechanical purity or original design integrity. Desert operations in North Africa presented yet another unique set of environmental demands, necessitating a distinct array of vehicle modifications. The ubiquitous fine sand permeated every mechanical component, drastically abrading moving parts and prematurely wearing out engines in a fraction of their normal operational lifespan. British forces, employing American M3s during the Western Desert Campaign starting in late 1942, installed massive air filters, some towering nearly 3 feet tall, specifically to shield engines from the insidious ingestion of sand. They also replaced the standard tracks with specialized desert pattern tracks, featuring wider blocks designed to provide superior flotation and traction in the soft, shifting sands. Water, in this arid theater, became an absolutely critical consideration. Vehicles operating deep within the Sahara routinely carried supplementary radiator coolant, and frequently towed trailers laden exclusively with water cans, essential for both maintaining engine temperatures and sustaining the crews themselves. The fundamental and overarching lesson gleaned from these myriad adaptations was clear. The half-track was not a singular, monolithic vehicle, but rather a diverse family of dozens of specialized variants, each meticulously evolved to survive the specific, hellish environments that would have swiftly rendered the original factory standard version inoperable within weeks. By 1946, with the war concluded, thousands of half-tracks sat idled in motor pools spanning from Fort Knox to Frankfurt, prompting military planners to confront an uncomfortable and pressing question: what was to be done with these machines? In this dark, brutal clarity of peacetime analysis, the half-track's inherent compromises became impossible to overlook or ignore. It occupied an ambiguous middle ground, being neither fully a truck nor truly a tank, and in the nascent world of the Cold War, this intermediate classification suddenly appeared to be a tactical dead zone, lacking clear utility. The Korean War, fought from 1950 to 1953, was widely anticipated to be the half-track's grand comeback tour. American forces dispatched M3s to the peninsula, expecting them to perform with the same efficacy they had demonstrated in the European theater. Instead, the Korean conflict starkly exposed every inherent weakness that the urgency and exigencies of wartime production had previously obscured or simply papered over. The rugged, mountainous terrain of Korea severely shredded transmissions and suspension systems that had been primarily designed for the more forgiving roads of Europe. The rubber track blocks, which had performed adequately in France, rapidly disintegrated on the abrasive Korean granite, often lasting a mere 400 meters before necessitating replacement. Maintenance requirements, too, proved to be absurdly demanding. A single M3 typically required approximately 40 man-hours of upkeep per week merely to remain operational, a stark contrast to the roughly 10 hours required for a conventional truck. Consequently, commanders increasingly opted to leave them in motor pools, instead requisitioning more reliable and less maintenance-intensive trucks. However, the truly decisive factor in the half-track's obsolescence was a profound tactical mismatch. Korean warfare featured unexpectedly longer engagement ranges, with infantry battles frequently unfolding at distances of 600 to 800 yards, a significant departure from the close-quarters hedgerow fighting characteristic of Normandy. The half-track 6.35mm side armor, which had barely offered protection against rifle rounds in 1944, proved utterly useless against the Soviet-supplied weaponry being employed by North Korean and Chinese forces by 1951. Even the 7.62 by 25 mm rounds from a PPSH-41 submachine gun could readily penetrate those thin sides at a range of 200 yards. Heavy machine guns, deployed by the enemy, effortlessly turned half-tracks into veritable Swiss cheese. Commanders quickly learned that deploying M3s anywhere near the front lines inevitably resulted in severe casualties among their soldiers. Concurrently, military engineers were busily engaged in designing something genuinely groundbreaking. The M113 Armored Personnel Carrier, which emerged from the Ordnance Tank Automotive Command in 1956, represented a complete antithesis to the half-tracks design philosophy. It was fully tracked, not a hybrid. It featured aluminum armor instead of steel, providing equivalent protection at half the weight, and it possessed inherent amphibious capability. Most critically, the M113 was conceived and designed from the ground up as a dedicated personnel carrier, rather than being an adaptation of an existing truck chassis. This new vehicle could effortlessly traverse rivers, offered significantly enhanced survivability against mine blasts compared to half-tracks, and its lower profile made it a smaller, less vulnerable target. The first production units rolled out in 1960, and by 1963, the message was unequivocally clear. The M113 undeniably represented the future of armored troop transport. The underlying engineering philosophy had undergone a complete and fundamental paradigm shift. Half-tracks were emblematic of 1930s thinking, taking established truck technology, appending tracks, and optimistically hoping that the resulting combination would function effectively. The M113, conversely, embodied the principles of modern systems engineering, commencing with a precise understanding of mission requirements, meticulously designing every component to operate in synergistic harmony, and optimizing the entire system for the actual combat environment it would face. The M113's Detroit Diesel 6V53 engine produced a robust 215 horsepower, representing nearly 50% more power than the venerable Hercules engine, all while weighing less and utilizing safer, more efficient diesel fuel instead of gasoline. Its advanced torsion bar suspension delivered superior ride quality and demanded significantly less maintenance compared to the half-track's vertical springs. Ultimately, a comprehensive cost analysis delivered the final, decisive blow. By the early 1960s, the expense incurred in maintaining the remaining half-tracks within the U.S. inventory cost more per vehicle mile than the outright purchase of brand-new M113s. Spare parts for half-tracks were becoming increasingly scarce, a direct consequence of their production having ceased entirely in 1945. Furthermore, the specialized mechanics, who possessed the intricate knowledge to service the old white motor transmissions, were steadily retiring. Meanwhile, M113 production was rapidly escalating, leveraging modern manufacturing techniques that significantly reduced per-unit costs to below $40,000, a substantial sum in 1960, yet economically favorable when compared to the ongoing expense of keeping 15-year-old vehicles operational. The international market echoed this sentiment. Israel, for instance, acquired hundreds of surplus American half-tracks in the 1950s and utilized them extensively, notably throughout the 1967 Six-Day War, but even they initiated a comprehensive conversion to purpose-built armored personnel carriers by the 1970s. Soviet forces completely abandoned half-track designs after World War II, transitioning directly to fully tracked armored personnel carriers, such as the formidable BTR-50. The French military retained their half-tracks for the longest duration, operating some into the 1970s in various colonial conflicts, though primarily due to financial constraints that precluded a wholesale replacement of their vehicle fleet. Ultimately, what led to the demise of the half-track was not battlefield failure. These machines, by and large, performed adequately within the technological and tactical parameters of their era. Instead, what unequivocally killed them was evolution. Modern warfare progressed at an accelerated pace, delivered harder impacts, and increasingly demanded specialized solutions rather than versatile compromises. The M113 and its subsequent descendants possessed amphibious capabilities, offered NBC, nuclear, biological, chemical, protection, could mount heavier weapon systems, and, most critically, were designed to keep infantry alive and protected in an era dominated by ubiquitous automatic weapons and increasingly potent artillery. By 1970, virtually every modern military had arrived at the same inescapable conclusion. The choice between tracks or wheels had become binary. The hybrid era, definitively, was over. The curtain had definitively fallen on what was once known as the hybrid era, a period characterized by ingenious, if ultimately transitional, military designs. The venerable American half-tracks, those iconic workhorses of a bygone conflict, finally ceased their active operational tenure with frontline units around the year 1964. This marked the conclusion of an impressive 23-year span, a quarter-century during which these distinctive vehicles had played an indispensable role in global military strategy. While some examples were creatively repurposed, finding new utility in various support capacities, their original and most recognized configuration as a dedicated personnel carrier progressively receded from the vanguard of modern armored formations. Indeed, the versatility inherent in their design allowed certain half-tracks to embark upon entirely new careers, transforming into robust engineering vehicles, vital recovery trucks capable of extricating other disabled machinery from challenging terrain, or even specialized mobile command posts, coordinating operations from a forward position. However, these secondary roles could not mask the fundamental obsolescence of their primary function. In contemporary times, the dwindling number of operational half-tracks are largely preserved within the hallowed halls of military museums or carefully maintained within private collections, serving as tangible mechanical fossils. They stand as enduring testaments to an ambitious epoch in engineering, a time when designers harbored the fervent, albeit ultimately unattainable, aspiration of forging a singular, universal vehicle capable of performing every conceivable battlefield task with equal proficiency. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. From a small town in the Midwest, USA, it's truly fascinating to observe how often the imperfect compromise in engineering emerges as the most critical solution during periods of intense global urgency. The half-track perfectly exemplifies this principle. It was never flawless, yet it was precisely what the world needed at its moment of greatest demand. Such an all-encompassing goal, as history unequivocally demonstrated, proved beyond the reach of the era's technological capabilities. Yet, for a critical and desperate decade, a period demanding immediate and effective solutions for troop mobility across varied and often unforgiving landscapes, the half-track's inherently imperfect compromise proved to be precisely the optimal solution. Its unique combination of wheeled speed and track traction offered a crucial advantage, enabling the rapid deployment of mobile infantry exactly when the world's urgent needs dictated such a capability. This pragmatic blend of attributes, despite its inherent limitations, was exactly sufficient to meet the extraordinary demands of that pivotal historical juncture.